Okay, guys, so we're going to dive a little more into the electron, okay, because the electron plays a huge role in determining what the atom can do. The identity of the atom is based on the number of protons, but what the atom can do and its abilities is based on the electrons. So before we can do that, remember how we talked about how the Bohr model has these energy levels? Well, what we've discovered in more recent research is that the energy levels are not the only thing that they have. The energy levels are broken down into sublevels that have orbitals in them. For example, the s orbital has the shape of a sphere, kind of like a basketball. It looks like this. It's three-dimensional, okay? Now, an orbital, okay, can only have two electrons in it. And the sublevel S has only one orbital in it. So 2 times 1 gives me a total of 2 electrons in my sublevel S. My sublevel P has the shape of a dumbbell, like the kind you would go to work out with. And in this p orbital, there are still only 2 electrons allowed in any orbital, and the p sublevel has 3 orbitals in it. So 2 times 3 gives me a total of 6 electrons available in the p sublevel. The shape of the D and F sublevels are not very important for our class. If you take chemistry in college, you'll probably go more into those shapes, but they only get more and more complicated, which means they require more and more energy. Now, there's still only 2 electrons allowed. An orbital can only have 2 electrons in it. The D sublevel has 5 orbitals, so 2 times 5 is 10, and the F sublevel has 7 orbitals in it, so 2 times 7 is 14. So when we talk about our energy levels, right, it's the rings around the nucleus, okay? The first energy level has only one sublevel. It has S, okay? The second energy level, or the second ring, has 2 sublevels. It has S and P. The third energy level has 3. It has S, P, and D sublevels available in that energy level. The fourth, fifth, sixth, and seventh energy levels all have 4 sublevels. They have S, P, D, and F. Okay, so while the Bohr model says that we have these kind of rings, that's not exactly a correct description of what it really looks like. Okay, but the way the electrons fill in these orbitals and sublevels and things along that nature are governed by 3 main principles. So we need to talk about those. The 3 main principles are the Pauli exclusion principle, the Aufbau principle, and Hund's rule. Now the Pauli exclusion principle says that 2 electrons, well, let's write it out. It says that there can only be 2 electrons in an orbital, and they have to have opposite spins. And they have opposite spins, meaning they have to face different directions. They can spin, one can spin clockwise and one can spin counterclockwise, but they have to have opposite spin. The Aufbau principle tells us that we have to put things in the correct order. So electrons will fill the lowest energy first, the lowest energy level first, and then move to the highest energy. So it'll start low and then go high, meaning it goes in a particular order. Okay? You cannot go out of order according to the Aufbau principle. Now, Hund's rule tells us that each orbital in a sublevel will get one electron first. So we'll have one electron before pairing up. Okay, and these rules will make more sense once you see them in action. Okay, but it's very important that you know which rule goes with what name. Okay, we also want to talk about what a valence electron is. A valence electron is the number of electrons on the outer energy level. So if I have an atom that has 4 energy levels, some of the electrons are on my inner rings and some of them are on my outer rings. So the valence electrons are the ones on the outside. And those are important because valence electrons are what you use in bonding. Anytime you have a chemical reaction, something blows up, something does something crazy, it's generally because of the valence electrons. Now, in order to see these rules put out into play, we need to talk about orbital filling diagrams. This is just a way that we represent an orbital diagram, okay? Or the way an electron fills up its atom. So each box represents an orbital, okay? And electrons are represented with arrows. These arrows can either be spin up or spin down. Okay, so we talked about how the s sublevel has one orbital, so we have one box that can hold 2 electrons. The p sublevel can hold 3 orbitals, and the d sublevel can hold 5. And the f, which is not drawn here, could hold up to 7. Now, if we look at lithium on the periodic table, we see that lithium has an atomic number of 3. The atomic number 3 tells me that I have 3 electrons. So what I'm going to do is I'm going to fill it in. I first start off with 1s, okay? My first energy level and my s sublevel. And then I have 2s. So 1 up, 1 down, 3. 3 arrows, 3 electrons in lithium. Notice that in my orbital, I only have 2 arrows, and that each box has 1 up, 1 down. This arrow is unpaired because I only have 3. If I look at carbon, carbon has 6 electrons. So when I fill this in, I would say 1, 2, 3, 4, and then here, this represents a p sublevel, correct? Because it matches what's up here. But according to Hund's rule says each orbital within a sublevel requires its own electron before they pair up. So in the s sublevel, they were paired before I moved on. But these boxes are connected beside each other, which shows that they're in the same sublevel. So I'm going to put my 5th and 6th arrow in opposite boxes, or in different boxes. It would be incorrect to put them in the same first box. They want to spread out before they pair up. It's kind of like if you have the option of not sharing a room with your little brother, right? You're going to each have your own room. The only reason why you would share a room is if you have no option. You have to. If we look at the next one, we have sulfur. Sulfur has 16 electrons. So when I fill this in, say 1, 2, 3, 4. I need to put 1 in each first, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, you may be wondering, how did we know when I should have an S sublevel and when I should have P's? Well, it goes back to Aufbau's rule that says there's a particular order. The order it goes in is 1s, 2s, 2p, 3s, 3p, and it continues in a particular order. Okay? Now, if we look at our periodic table can help us determine that order. An energy level is the same thing as a row on the periodic table. So row 1 represents energy level 1. So we have 1, 2, 3, 4, 5, 6, 7 rows on the periodic table, just like we have 7 energy levels. We can also see that the structure of the atoms, not the structure of the atoms, the structure of the periodic table can also show us how the sublevels are arranged. Now, column 1 and 2 represents the S sublevel. Now, the S sublevel we know can hold 2 electrons in it. Each box represents 1 electron. This center part, 3 through 12, is the D sublevel. We know that the D sublevel has 5 orbitals for a total of 10 electrons. And we can count it and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons, 10 boxes. Column 13 through 18 represents the P sublevel. We know that the P sublevel has 3 orbitals, 2 each, for a total of 6 electrons, and there's 1, 2, 3, 4, 5, 6 boxes, because every time I go across, I'm adding an electron. Notice that I did not include helium in the P sublevel. That's because while helium acts like the rest of the noble gases that are in column 18, helium's electron configuration actually belongs in that empty box right over there by hydrogen. It's part of the 1s level. And then these down here, the lanthanide and actinide series, are part of the F sublevel, which have 7 total electrons. Now, the first 2 boxes actually belong right here where the stars are. So if we count, starting with thorium, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which is the total number of electrons we would expect in the F sublevel. Now, to figure out the order, you just read the periodic table like a book. Now, when you're reading a book, you start from the left top part of the book and you go across. So if I were to read this like a book, I would start here and I'd say 1s, and I had a total number of 2 boxes, hydrogen and helium, so I put the number 2 as an exponent, and that takes care of my first row. Whenever you're done reading one line on a book, you go to the next one. I'm starting at energy level 2, sublevel S, and there are 2 boxes. So it'd be 2s2. I keep going and I get to the P sublevel. So I write 2p6. I would then go on to the third energy level, 3s2. Keep going. I get to 3p6 because 1, 2, 3, 4, 5, 6. Pass through them all. Start here, energy level 4, sublevel S. There are 2 boxes, so I put the number 2. But when I get to the D sublevel, that's when things get interesting. For the D sublevel, you have to subtract 1 energy level. So you subtract 1 energy level. And so what that means is instead of this being 4D, 4 minus 1 would give us 3D. So it's actually 3D 10. And if I keep going, I will hit the P's, and now I go back to my 4p6. And you can keep doing that until you fill up the entire periodic table.